So I'm Alex. I'm in the math department in data science at UCSD. I'm not a card-carrying statistician, so I promise that this will be, maybe y'all will know more about this stuff than me. I don't know. OK, so just as like a quick overview, collaborators, Timo, former postdoc in my group, Shu, colleague at Duke. And a lot of the work will be from Varun, who's a grad student that worked with me, just finished his PhD. So this is like very fresh stuff. I think he just defended it last week. Yeah, he'll be a postdoc at Brown next year. And also, if you ever run into Varun, he's great. He's like one of the best grad students I've ever worked with. So anyways, what do I want to talk about? So funny enough, I'm really glad that Adit went before me because I won't have to justify like the first 10 slides. So basically, what I want to think about is deep learning. I come from a manifold learning background, so I'm really interested in questions of like dimensionality, right? How does the dimensionality affect your problem? How does the curse of dimensionality show up? How can you get around it? So I originally came into neural networks from like an approximation theory perspective. I'll talk a little bit about that here, but then I'm also going to talk about stuff related to like neural tangent kernels and what you can say statistically. So the thing is that most like approximation theory about neural networks basically say that the size of your network you need is going to grow somehow with the number of points and the amount of error that you want. And it's also going to be dependent on, at best, the intrinsic dimensionality of your data. Which I want to argue is already too pessimistic, right? So this doesn't really explain in practice why, one, I mean, neural networks can learn simple functions easily, obviously, right? Also, and this is also what I'm going to talk about a lot in the second half of the talk. Neural networks incredibly quickly learn statistically powerful biases between your distributions. And so I want to kind of characterize that a little bit more. And they work even when the intrinsic dimensionality of your data is massive, right? So the focus of the talk is going to be that. It's a survey of some work that I've done over the last few years. Again, it's approached from a couple different angles. So some will be a little bit more, functional analysis, approximation theory stuff. Some of them will be more statistics. Some more just, NTK type analysis. And my point I really want to get through is two things, which is one, that the complexity of the function plays just as important of a role, if not a more important role, than the actual dimensionality, right? And I want to characterize that a little bit. And then also I want to talk about the fact that like simple deviations in distributions are incredibly easy to learn and will be learned incredibly quickly, right? So that's the statement. All right, I don't even know why I left that in there. This is a neural network. OK. So there's like a couple basic results that, if you're familiar with sort of expressivity of neural networks, are pretty obvious. The first says that if you're trying to learn like Holder functions on some capital D dimensional space, then basically there are going to be neural networks that can learn these functions when the neural network is sort of a sufficient depth that's not too big. It's sort of log in the error that you're looking for. And the width is going to be sort of on the order of the error to the ambient dimension over some smoothness parameter. So that isn't going to work in some sense, because we're talking about problems that are 30,000 dimensional, problems that are 50,000 dimensional, like 100,000 dimensional. The size of the width is 1. Or infinite. I mean, sorry. You have epsilon to the huge, minus huge number, so it's infinite, right? And similarly, there were just basic results. This was actually what got me interested in neural networks. This isn't what I'm going to focus on in this, but they'd say, all right, if your data lives on some nice low-dimensional structure that has k dimensions, k intrinsic dimensions, then basically all those d's can be replaced with k's, right? And that you just get this very, very tiny dependence on the ambient dimension. Fun story on that. This was like the first thing that I ever was interested in neural networks, and I worked on it because I wanted to prove that neural networks, this was like in 2014, didn't work in super high dimensions, because I was like, they're half spatial approximators. How is this going to work? And so then you can prove that they do, and OK, fine. So all right, what I want to look at is a slightly different model. And that model is, I want to think about data. All right, fine. Maybe it fills an ambient dimension. Maybe it lies on some low-dimensional structure. Maybe it lies near some low-dimensional structure. But what I really want to think about is not the dimensionality of the data, but what I'm going to call the dimensionality of the function, right? And this is basically a generalization of the multi-index models that Adit was just talking about. I want to think about a problem where the function I care about is invariant to movement off some manifold. And I'm going to use the word manifold here in like huge air quotes, okay? We can talk about unions of manifolds. We can talk about, almost everywhere it has some nice tangent bundle structure. Maybe there's some singularities. We're just going to ignore those. Like, this can be a lot more general than, smooth Riemannian manifold. But basically, I want to think about my dimensionality in terms of how the function is invariant. Okay? So I'm assuming that there is some structure that I can project onto where the function only depends on the projection onto that structure. Okay? The data can be space filling. And that's actually the dimensionality that I argue governs the complexity of your problem. Okay? And this works in a couple of settings. And the first one was one that I was just kind of curious about for a long time. Again, I come from like a manifold learning community, and we were always interested in what happens when you have data near a low-dimensional structure. And like, what does it mean for the data to be sort of kind of intrinsic dimensionality low, but in reality it fills everywhere, right? I think from this perspective, it kind of answers this question really easily. I actually don't care about what near a low-dimensional structure means. I'm encoding all of that idea, like the idea of near a low-dimensional structure hides an implicit assumption. The assumption is that the task you care about didn't depend on the normal directions. Right? That's what I'm interested in. And so if you define it that way, where you say, all right, I'm going to assume there exists some model where I can project onto it, and then the function depends on that, this will allow you to talk about the case of, messy data that isn't exactly low-dimensional, but maybe close to. Equivalently, you can talk about things like multi-index models, right? Living near some union of subspaces. Again, you talk about projection on the subspaces. You can then talk about, a sum over several manifolds. That's what your function depends on. You can talk about invariances in this way, obviously, also, right? Like, you want to project onto something where you're finding a representative element of some set of push forwards, right? And then just the function really only depended on that representative element, right? So in all of these cases, you can say something pretty. Sorry, I should have said. I kind of put an amalgam of slides together, so. If I forget what's on the next slide, it's because this just came up very recently. The only thing I want to mention is like, what is the assumptions we have to make on the data itself? So really all we have to assume is that you have some type of projection, right? So you're within the reach of whatever your manifold or set of subspaces, union of manifolds is, right? As long as your data lies inside of there, inside of that reach, you're going to be totally fine to state the following results. And I'm not going to go into the proof of these because, quite frankly, they're not that elucidating as far as really trying to get through the overall idea. But the statement is pretty obvious, which is that similar to the other settings, if this is your case and your data really is high dimensional, the size of the network you need to learn these types of functions is actually quite small. And it only depends on the assumption that my function was only defined by its projection onto some low-dimensional subspace. Or low-dimensional manifold. Okay, I don't even know what that low-dimensional manifold is, right? But that's all I need. Yeah.
Is your definition of like nice? I mean, it's not.
No, I'm putting nice in quotes there. Yeah.
Basically, so nice is that.
Yeah, so nice is really that you can think of it as like locally smooth, right? Okay. But then at the same time, this is sort of an informal statement. You can very easily break this up into like a union of locally smooth manifolds, right? And then I have this comment right here, which is like all of the analysis to prove any of this is entirely local. So what that means is if instead of dealing with infinity norm, you want to deal with some 2-norm thing, so you're allowed to throw away a few points that like I'm never going to classify them, you can easily do that and generalize to something that just satisfies what you can call like a local manifold structure, right? So this easily applies to, say, data that lies on a square or something like that, right? Yeah, so that's the statement. And then the one other statement I want to make about this, which I also found kind of fun, which is that you can also think about this problem not for regression, but for classification, right? So in classification, what's the model that you want to think about? A very easy model is to say I'm going to assign a class label to my point based off of basically nearest neighbor, right? This is actually how we deal with a lot of classification problems, right? You have clusters. Each cluster has a label. You're really labeling just based off of your distance to a centroid, right? So again, in some sense, this is a morally very easy problem, right? It's a basically zero-dimensional problem. You only need to worry about these few isolated points, right? And so you can set up functions in the same way and say, all right, if we care about functions that sort of really only depend on the projection onto some set of classes, right? These are easy if the classes are sort of morally low dimensional. What do I mean by morally low dimensional? I mean that if you want to build a delta epsilon, or sorry, if you want to build an epsilon cover of your class set representative class elements, you need epsilon to the minus k points to do that, right? Morally low dimensional. And again, you can state the exact same statement, right? And what this says is that if you're really trying to work on a problem of like isotropic clusters, you don't need a neural network that's larger than 1 over epsilon, right? Similarly, distance, if it really only depends on like how close it is to a few different lines or something like that, so your classes are like tubes or something. Again, it doesn't, you really don't need anything more than 1 over epsilon size network, right? Yeah, so this is just kind of a, and I should say it doesn't even have to be distance in like 2 norm. Pick a norm and, similar things can be stated. So I say this all to say that like, I basically became more and more convinced that like the complexity of the dimensionality of my data is the wrong thing to look at, right? Let's look at some other notion of dimensionality. So, and I should mention, this is the parameters. Similarly, just using very standard, empirical risk minimization estimates, you can talk about how many points you need to learn these types of functions, right? And the number of points in a statistical sense is very, very, very small, right? Now, this is not dealing with the optimization of neural networks, right? This is, the existence, there exists an empirical risk minimizer, stuff like this. Yeah.
If we can go back 1 second.
Yeah.
Does that alpha actually appear anywhere in that inequality, or?
It's just right here.
It's over there. Okay.
Yeah, if your functions are wildly non-smooth, these are like alpha holders, so if alpha is super close to 0, then like you can get some strange stuff. Yeah, yeah. And by the way, I didn't even mention in this that I mentioned this comment about like the reach, like as long as your data sort of exists within the reach of this generalized manifold. As you get closer and closer and closer to that reach, all of the constants in these kind of get really bad if you're trying to bound the infinity norm, which is not shocking, right? Okay, so those are the quick statements. So now I want to mention one more thing that I think kind of merges topic 1 and topic 2. And though this was something I was actually working on independently when I was kind of curious about these neural networks, how complicated your function is. And that is two-sample testing. So what is two-sample testing? All right. First off, it's something I knew nothing about until I was a postdoc, because I never took any statistics. But now I do enjoy statistics, let's say. All right, very simple question. I have 2 point clouds, finite samples. Did they come from the same distribution or not? That's the question, right? So the null hypothesis, they came from the same distribution. The alternative hypothesis, they didn't. There are 1,000 different ways to try to address this question in a whole bunch of different contexts. There's kernel maximum mean discrepancy, there's optimal transport, there's KS statistics. I'm going to focus on classifier two-sample tests. So what's classifier two-sample test? It says, I want to learn a function that is going to get some non-zero integral when I look at p hat minus q hat. So that implies that I can start to differentiate which class my points came from. Did they come from distribution P or did they come from distribution Q? If I can learn a classifier that gets anything better than random, then P and Q couldn't have come from the same distribution. And we can be statistically rigorous about this, right? So as a note, I kind of like to joke about this. Supervised learning is like an easy version of a two-sample test because the distributions are completely separate from one another, or hopefully, right? We can talk about things where the distributions are almost on top of each other, but with marginally different tails or something. So you only get a little bit of a bias. But even finding that little bit of a bias will allow you to state that these didn't come from the same distribution. And two-sample tests show up in a lot of places, including generative models, right? Every generative model is basically running some type of two-sample statistic between the generated data and the original data, right? GANs are doing this with a classifier statistic, right? VAEs, Wasserstein GANs, these are doing it with a whole bunch of different types of statistical distances. So we wanted to play around with this just very simple idea and just ask the question. This is not with Timo, this is with my colleague Shu. We wanted to ask this very simple question of like, okay, I want to use like a logistic output neural network, right? And I want to see if I can use a neural network to determine, did my points come from distribution A or distribution B, right? If I can get any power in this, maybe, or any bias in this, maybe I can say something about whether or not, statistically valid results about like, oh, these came from different distributions, they came from the same distribution. So you have some classifier. This yields what I'll call like a witness function, which is basically if you look at the log of that, you take this, u theta minus v theta. So how does a classifier two-sample test work? You train, you split your data that you have available into training and testing. You train on the training. You develop your statistic on the testing because it's independent. And then that statistic is what you use. I'll describe in a minute how you decide like whether to accept or reject using a permutation test. But at the end of the day, this is what you're doing. And it turns out that if you look at like the population training objectives of using a logistic neural network and cross-entropy loss, this is like the population level thing you're trying to do, which is basically just Jensen-Shannon divergence between the distributions. So really what you're trying to see is if if you can truly attain the maximum there as you're training, you're basically just trying to see if you're trying to match the Jensen-Shannon divergence between these two distributions. And then the test statistic you're going to use is basically the accuracy, right? The output of the neural network, even before you apply the logistic part, right? Just is it positive or negative? Evaluated on the test data, that's your statistic. You can show the statistic is basically bounded below by this Jensen-Shannon divergence term. And so the question is this non-zero? Because if it's non-zero in a sort of way that was different than if P had been equal to Q, then you accept or you would reject the null, right? And so you can make some very simple statements about things like what if you have data or two distributions and they lie near some lower dimensional structure. So near in this case is going to mean that there's noise and that noise has an exponential decay moving off manifold. Yeah.
So is your space perhaps like smooth, or is it just a very general? In the previous slide, minimizing over F. Yeah.
Right. No. Yeah. So in practice, that F is a neural network. Right, yeah.
So otherwise I was going to ask the question, like, is this like just a very complex calculus of variations problem? But I guess not.
No. In this case, that F is a neural network. Right. So that is actually, and that's actually the class we're going to work over, which is basically Lipschitz bounded neural networks. So that just means that you're making sure that the product of all the weights is not infinite, right? Or bounded, right? So using that, you can find some, and again, these are sort of approximation theory type results, but they start to lead to some interesting statistics, which says that, okay, easily you can build neural networks with a complexity that depends on the intrinsic dimensionality, such that the loss on that neural network is going to be bounded below by something that's hopefully non-zero. It's sort of the Jensen-Shannon divergence is like the property of the problem, right? Were P and Q equal? If not, how different were they? And then all of these terms that are sort of, there's some statistics, statistical estimates and approximation theory stuff. Don't worry about all of the terms there. More or less what you get is, again, now you want to do this on finite samples. You can bound this in a way from what you would have had if you had infinite number of samples. And this is really the meaningful thing, which is that if you're using neural networks, there exists some neural network in a class of neural networks that aren't that big, right? That would have had close to 1 power to differentiate. Right? And when I say power here, what I mean is you have a null hypothesis, you set your alpha, that gives you a number, and then you're asking whether the alternative is above that number. Right? The power asymptotically goes to 1. So I put those two things together to now move towards the next part of my work. And I want to just kind of tell you a fun story here. Right? So Shu and I wrote that paper about logistic neural networks. And we demonstrated it on a few two-sample testing problems. And it works, and it's nice. And we enjoyed the theory, and we published it. But a year later, Shu was writing a follow-up to this. And there's this problem in the two-sample test community that's kind of known as like a very hard problem. And the hard problem is the following. You have two distributions, P and Q, that are different. P is a Gaussian mixture, and Q is a Gaussian mixture at the same means and with variances in 2 dimensions that are just kind of anti-skewed. Okay? Now what that does is the first 2 moments of P and Q are identical to each other. Right? And so now you want to still distinguish whether or not P is equal to Q or P is not equal to Q from finite samples. And that's not, it's kind of a hard problem, right? So here's what was funny. She wrote this paper about a year later and submitted it to, NeurIPS, I think it was. So it's a double-blind review. And the review comes back and says, this other thing you're doing, it's fine as a two-sample test statistic, but it doesn't match the state of the art of two-sample test statistic literature using a logistic neural network cite Schuenmein's paper. And we were like, I never really thought about this empirically. We kind of did. We did some basic experiments. But we didn't do a thorough comparison. And it turns out that other people had. And it turned out that this really is sort of the best way to distinguish P from Q, even in this problem. But there's a caveat to this. The bounds we had are way too pessimistic. And beyond that, I'll show you in just a sec. Oh, yeah, let me mention one thing, and I'll show you the meaning of the result. All right, how do we determine the power, right, in a real way? Again, something I somehow didn't learn until I was a postdoc, which makes me very sad. I think this is like the most interesting topic ever. Permutation testing, right? So what do? You have P and Q, you get out some numbers, you get your statistic. Great. Now you're going to take all the points you ran that statistic on, throw them into a bag, redraw them, and put them in either P or Q, right? So now you have a null model. And then you compute your statistic. And you get a histogram of your statistic. And then you say, does the actual statistic exist at the tail of my null? Yes, reject the null. No, accept the null. Right? Fail to reject the null. And so that's like the basic idea of a permutation test. But let me show you what's really cool about this. This is that really, really, really hard problem. Okay? The Gaussian mixture. We're going to use a neural network to try to distinguish P from Q. And when we do it, we then run a permutation test to say, should we have rejected the null? Okay? And we're going to do that 1,000 times for each one of these cells. So the x-axis is the ratio of parameters to number of training samples. So these are small networks. I go beyond to up to 2, but some of these networks, 0.01, right? Very small networks relative to the number of points. And this is the number of epochs that we train. Very small, 1, 2, 3, right? What you see is that these classifier networks using some just simple neural network, very small neural network, are insanely powerful when they're small and after a very, very short time of training. That does not agree. I mean, it did not agree. That is not explained by what I stated previously about all the approximation theory stuff. So what's happening here is you're not letting the training error go to 0 at all. Letting the training error go to 0 is actually nonsense in a problem where 2 distributions lie on top of each other, right? You're just running it just for a minute and then checking. And so this was kind of the question that we were interested in. And to people that are familiar with the NTK literature, maybe this is not shocking, right? And it wasn't shocking to us either, if you think about it from that perspective. Yeah.
So you had a compound alternative, right? It was P not equals to Q.
Yes.
So how do you calculate the statistical power?
Again, just through this permutation test. So.
But against all
Oh, sorry. Yeah, P and Q being absolutely continuous distributions, like bounded moments. I'm not thinking about insanely.
So you're
hard
limiting the size of
yes,
the
yes,
of
yes.
the alternative. Okay.
Yeah. Things I can distinguish under this integral probability metric. Yeah. Thank you. That's a good point. Okay, because actually the reason I mention this is that to answer this question, we're actually going to have to play around with what is the alternative we care about, right? Even more so. So we saw this and said, well, this isn't maybe too surprising, right? Because if you just do a lazy training regime analysis of this, very quickly, you're going to start to learn functions projected onto low-frequency eigenfunctions, right? And so our question just became, can we talk about this from a two-sample test perspective and say something about the power, right? And basically the problem was classification accuracy, trying to get zero training error is nonsense here, right? In fact, it's going to be massively overfit, right? And also, like, yeah, so training error going to 0 is complete overkill. So we just wanted to say, all right, we're just going to have error that just needs to decrease just a little bit. As long as it decreases just a little bit, and like in a clear way, you have a statistically good test. And so we do this through looking at just like a subset of NTK moments, very early stopping, very small networks. And it just requires a little reformulation of the way that we normally think about this analysis. And so I just want to mention a couple of things, which is that originally I was talking about logistic output. You can do this with a linear output as well. It actually makes no difference, right? So these are just linear output neural networks. You have data sampled from P, data sampled from Q. You train with an L2 loss. It turns out that at the population loss, that's equivalent to training a neural network against, if you truly had this, it would be P minus Q over P plus Q, where those are the densities, right? That would be kind of the function you're trying to learn in the population. And so now we're going to ask this question of, the two-sample testing question. Train on a training set, have a test set. And we also want to just talk about like a population level statistic, if you had an infinite number of points to train with. We're going to encode the dynamics of training. We're going to train through basic gradient descent. And the thing here, I'm not going to say I can distinguish any H1. I actually just want to deal with easy problems. Okay, because it turns out, like I said from the first part of this talk, a lot of times how complicated your problem is just related to the task, not to the dimensionality of the data or anything like that. So it turns out that problem, even though it looked really, really hard, like the hard two-sample testing problem, there are regions where you have a lot more points from one distribution than the other. So you just kind of have to isolate those, and you'd have a good statistic, right? It's not that hard. And so what we're going to talk about is basically an alternative that's it modulates. So what it's going to be is that we can't necessarily distinguish any P from Q, but we're going to distinguish when P from P minus Q lives on some low frequency subspaces. And I'm defining low frequency here by just eigenfunctions of a particular infinite size NTK. And so really what we're doing here, it's kind of simple, right? Rather than trying to analyze when these things are going to 1, which is not relevant, I just care about when it deviates from 0. That's all, right? And so you can do this. You can talk about the finite samples. You can talk about a statistic trained on your training data, evaluate, extending it to test data. You can talk about it on a population statistic, and then we'll have. I'm not going to go into the analysis, but I'll show kind of the key theorem, which is very simple. But you can talk about, this is sort of what's really happening, and then these are like auxiliary dynamics. This is the dynamic if you're truly training on an infinite amount of data. There's an auxiliary dynamic on like the 0-time kernel on an infinite amount of data. And then everything we do is explain these, which are really, really easy, and then use some concentration inequalities to say that these can't deviate too far from those. That's it. And so the real thing just comes down to this simple statement, which is that if you have a desired detection level, right, and you have some desired what I'm going to call time separation level, I'll explain that in just a second. And I'm going to assume the F star, which is basically P minus Q, the true deviation between the two densities, has a large enough norm on the first k eigenfunctions. It doesn't need to be a low frequency thing. It just needs to have some non-trivial projection onto the first k eigenfunctions of some NTK operator. If that's the case, then with high probability, it's very easy to say that basically the min detection time under the null model. Now, if we're doing this on an infinite amount of data, the null model is 0, so this would actually be infinite. But you can also do this for like a finite number of points, because obviously we know that you'll eventually get accuracy of 0, or an error of 0 on the training data, even if they came from the same distribution. But that time minus the min detection time under this assumption that we have some projection onto the first k eigenfunctions. is positive. So what that means is if you're training and you live in this time window, you'll get a really good statistic. And you can state it pretty easily, just a slight alternative of this, the epsilon over 2. That's the time it would take for the null model to accidentally get an epsilon over 2 deviation, epsilon over 2 power, or epsilon over 2 statistic, like how quickly did it leave 0. If you train for any time in here, it turns out that using a neural network, that neural network that you instantiate, it's going to be a really, really powerful test. Yeah?
So your alternative here is pairs P and Q, for which if you look at the projection of the difference, then the norm of that projection is large. Is that what you're saying?
No, it's not even that the norm has to be large. It's that if you look at the difference and the inner product of that difference with a couple of low-frequency eigenfunctions of the NTK, it has to be non-zero. It has to be at least epsilon. I have to at least epsilon of the energy of that deviation had to kind of have a low-frequency component. There can still be a lot of other craziness going on.
Yeah, well, the reason I ask is like in this two-sample literature, what people look at is how that epsilon depends on n, right? Because that's, if you fix delta to be, let's say, order.
I agree.
Then it's of interest to say how small does epsilon have to be.
So I agree. What I'm doing here is a little different. The epsilon is actually a property of the continuous problem.
Yeah.
And now what I'm going to do is talk about what the finite statistic would do.
So you're doing the inverse of this.
Yeah. So it's that, in some sense, that the assumption I'm making there is a property of my problem. There are certain problems I will not be able to solve. I'm just throwing those away, right? And so that's what it is. And then what you can say is, I guess I've got a few more minutes, but let me actually just kind of get to what I'll answer that question in 1 second. All right, so how do you do this? You think about the population level thing, if you didn't have a finite n. You can write down very similar statements about training dynamics. And now what we're saying is I'm not caring about going to the norm of f star, which is trying to get like perfect prediction of f star. That's never going to happen. I'm just caring about what happens in the projection under the first few eigenfunctions, right? You can describe the dynamics as a function of time, eigenvalues, all of that. And even there, I'm only going to assume that there's a small subset of the eigenfunctions of the NTK on an infinite number of points, such that, the projection is non-zero. Right? And that, this is getting back into my own language, right, of manifold learning, right? Eigenfunctions of kernels, simple things. And so, this is not, I'm not claiming this is like an easily checkable hypothesis. It's not, right? But it is I claim that this is actually a property of most problems. Most problems in this literature actually do wind up having this component at least be non-zero. And so the other thing is that in describing it this way, I'm actually kind of untied to whether or not my neural network has an infinite number of nodes or not. Okay? Because if I had an infinite number of nodes, then I have a dense spectrum in this NTK operator. If I have a finite number of nodes, I don't. It's low rank, right? But I don't care about that. I only care about the first few, right? So we can talk about small neural networks, and it actually leads to kind of a question that I'm sure someone in here is going to be like, oh, that's a very easy question. Because again, I'm not a random matrix theory person, but I think this is a pretty easy random matrix theory question, or a straightforward random matrix theory question. It would basically be, how small can my neural network be, like the rank of this kernel, such that for most problems that I care about, there's just going to be a little, some of the energy will project. So it's this question of like, will this NTK operator pick up, how big does it have to be such that my deviation does not entirely live in the null space? Okay? And so, basically, once you have that, then you can set up a pretty simple analysis. All of your analysis doesn't depend on the minimum eigenvalue of your NTK. It just depends on the minimum eigenvalue of these couple of eigenfunctions that help me describe my deviation. Okay? And so now what you get is like if the population is greater than epsilon, then all of these empirical ones are going to be greater than epsilon minus. There's a little approximation error in time, and then there's a little concentration error of like infinite to finite. I won't go into what those are, but they're pretty straightforward. Matrix Bernstein inequalities, pretty simple analysis of sort of if you've trained and your population would have been at epsilon, then your empirical one probably would have been, the amount of time it will take to get to epsilon is not much bigger, right? And so you get these bounds, and if I'm honest, I'm not even going to bother with that. So what do we get? We wind up getting all these constants where you can write out explicitly the theorems, the constants, the probabilities, everything. They come down to a couple of very simple things. So one is going to come down to, well, you know what? Actually, I should have said something here. I should have said one thing. Sorry. What we're relying on here is the fact that you're in a lazy regime, right? So you had an initial NTK, maybe there's some low-rank thing, and then you train for a little bit of time. And you can bound sort of how far apart those things are going to be as a function of time. I don't need to train for a long time, right? So I don't need big neural network. I don't need to train for a long time. So all of the complexity that we had of making sure of figuring out when we're in the lazy regime, when we move to an active, I don't have to worry about that, right? That's kind of the nice thing of thinking about this two-sample test problem. And so you can say, you can get things that are bounds in terms of sort of how much you deviated from the initial time NTK. And there are all these constants that show up, and I want to highlight them real quick, just because it kind of helps give a proxy for all of this problem. One is related to the Lipschitz constants of our neural networks that we're using, and kind of related to like how many neurons we had in our neural network. And those constants hurt us. So there's an interplay here. The smaller they are, the smaller the neural network is. The longer I can, basically the smaller the neural network, the better I can get, so some zero-time approximation. It won't be too bad of a model. I've got sample sizes that I have to worry about. It's fine. But then there's this f star, which is, again, p minus q over p plus q. The detectability of this depends on how much I project onto the spectrum of k0. So the harder the problem is, the more complex the network has to be. And there's this interplay of these two things, right? And yeah, I mean, this is not a full answer of like I can now create a perfect bound on the curve of where the power goes to 1 in that hard problem. But I think this is a start. This is using the same language that I think a lot of us are already familiar with to then just describe a rough idea of why this is actually happening, right? And so I'll just kind of conclude here. But my takeaway that I want to mention is I think both of these, the reason I paired these things together is because I think they both, or all three, I guess this is 3 papers, hint at the idea that we should do a little bit more analysis of our models, not from the perspective of our data, but from the perspective of our task, right? If our task is easy, we don't have to go crazy with it. It's very similar to what Adit was talking about, right? And then the other thing is, from a statistics perspective, neural networks make really, really good two-sample test statistics. Really good. Shockingly good. It was insane to me when I thought about it, just if I'm honest, right? Because like a neural network overfits the training data, so you'd think that would be horrible for statistics. But somehow it's really good. And you don't need to train it for a long time, and you don't need big networks. Obviously, in certain problems you do. If you're doing classification, you do. In my context, you don't. Right? So found that to be kind of interesting. So with that, I'll go ahead and stop. Yeah, thanks.
Definitely have time for some questions.
I went quick.
Yeah. Back like 3 slides.
Yeah.
Yeah. So in here, this also first off for context, all my questions are stupidly vague. But okay, so this looks like this looks like some kind of concentration inequality-esque thing that makes me wonder, like, are there higher order terms like nq to the power minus 2a or nq to the minus 2a on bullet point 2 that you can add to that, perhaps? Like, I don't know where that.
I bet, yes. It comes from a matrix Bernstein inequality that's basically saying that like when I evaluated the infinite NTK on finite data,
Okay.
I'm not
so
going to be
this
too
is
far
like an
off.
approximation of some bigger.
Yeah.
Okay.
Yeah. It's like, given the actual data that I sampled, how close is that to the mean?
Can you go back to slide 3, I think?
Number 3?
Yeah, that might be wrong. But,
I'd be impressed if you.
no, okay, definitely wrong. Slide 7.
Give me what it is, and then maybe
yeah,
I can.
I mean, maybe this is it.
This is like, this has nothing to do with functions. This is just.
Can this condition on manifold be like relaxed so that like I want to ask if that e to the -1 can become e to the -2, then what should the word manifold be replaced by? Which is again like kind of a vague question. That makes sense.
That's an interesting question. So you're saying if you want to have a smaller network?
Or yeah. So not smaller, but I guess like I want to take that e to the -1, and I guess the general question is I want to replace e to the -1 with some arbitrary other like
The like here.
Yeah.
Here.
Or the epsilon to the -1. I was just thinking yeah. So like we know like we have this coupling of like manifolds to this like nice 1/e, 1/error error dependence.
Yeah.
If I want to replace that 1/e with something else, then what should I change this?
No, that's a good question. Honestly, and this actually does kind of relate to what I was just saying, to what I was saying in the two sample test stuff. This is about like Holder functions.
Yeah.
If you flip this to being like twice, 3, 4, 5 times differentiable, that whatever the number of derivatives is basically just shows up here. So if you use smaller networks, you can learn smoother functions.
Okay.
And there's a very simple interplay there. But yeah. I don't know if that answers your question. That's not an assumption on the data, it's an assumption on the function. So I can't necessarily say for assumption on the data. The data I really view not as having, the epsilon doesn't come into play, it's really just the dimensionality. So I don't know what it would be to replace it with.
So I guess like my question is just like manifold's like a very partly restrictive term here. Like if there's like, for coarser or like shittier sets, could we still produce inequalities like this?
I see what you mean. In this one, no.
Maybe with your alpha holders.
Yeah, this stuff, yes, I think the answer would be yes. I haven't, but I think it would be. If I were to go into like how you prove this, it just has to do with like creating these like tubular regions where you're assuming the function isn't really varying too much, and then it's about sort of how many points lie in that tubular region. So if you went more complicated,
breaking up your set into components where it is nice, and then depending on what the structure of that component is, controls what this inequality.
Yeah, if I'm being honest, the biggest issue you run into is that some of the stuff to prove this requires partitions of unity, which I think would run into issues if you're dealing with more complicated structures.
I'm not familiar with that, but
yeah,
I can believe
it has to do with like defining little indicator functions on charts such that the sums more or less are constant.
Okay.
Across it, if you pick a point. So maybe it's possible. I'd be interested. Yeah.
Epsilon to the -k over alpha is related to, or it's exactly the infinity packing number, right, of the alpha holder class on a k-dimensional level, right?
I don't think about it that way, but yes, I think so.
So I guess my question, the reason I asked that is can I replace alpha holder with an arbitrary function class and get something related to the entropy of the?
Yeah, I think that would definitely be possible. I don't.
Oh, you're not sure.
I'm not sure. I think that would be very attainable. Let me put it that way.
Because your argument sounds like you're.
Yes, it's honestly, half of the argument of what I'm talking about here doesn't even really need to apply to neural networks. There's a lot of functions. There's a lot of models where you can do something along these lines. Actually, the type of model that Adit was talking about, which is kernels with some sort of like Mahalanobis distance, if you defined a localized version of the Mahalanobis distance, it would basically, this result would just be like plug and play.